Okay, so this is the first of a few lectures that I want to give on nonlinear problems. So the bad news really is that the world is nonlinear, that when you think about linear equations, let's say the Laplace equation or the Stokes equations, that these are all approximations, that this is not how the real world behaves, and that in all of these cases where you have a linear equation, really what it is you make an assumption that something is small. So let's say in the Stokes equation that the velocity is small, or let's say in the Maxwell equations for electromagnetics that the let's say field strength is small. In all of these cases, this assumption may be valid in a particular situation, but in general, if you want to look at problems that, let's say, describe the world in realistic terms, the world is not linear. And so all of the equations that I've shown you in the first 30 or so lectures, they really were only approximations to how the real world works. So, I mean, to give you a few more examples, the Stokes equation becomes nonlinear in the case where velocities are high. In that case, you get the Navier-Stokes equations. If you want to think of, let's say, the elasticity equations for, let's say, the deformation of an object, if you consider large deformations, you get a nonlinear elasticity equation, so let's say a hyperelastic equation or a plastic equation. So the question in all of these cases is, how do you actually solve nonlinear problems? And so what I would like to do in this first lecture is that I go through this process of, let's say, how do you arrive at a nonlinear equation? I'm going to give you two examples. And then I'm going to show you a few of the techniques that we commonly use to solve nonlinear partial differential equations. And they're, of course, informed by what we do when we just want to solve nonlinear, let's say, algebraic equations. And then in subsequent lectures, I'm going to talk about one of the, let's say, best methods that we have. That's the Newton method. And in the one after that, how to apply that to a particular problem, a model problem that I'm going to show you here in a few minutes, namely the minimal surface equation. So that is step 15 that implements this. So without further ado, let me go over a few of the examples that we have. So this is lecture 31.5 on nonlinear problems. So like I said, the world really is nonlinear, and if you do happen to have a linear equation, there is almost always an approximation that, or an assumption that something is small. So for the Poisson equation, we typically consider the Poisson equation to be a model for the vertical displacement of a membrane, so let's say a drum or something like this. So the Poisson equation is linear, and the assumption behind that is that the vertical displacement of the membrane is small. In the Stokes equation, the assumption is that you have slow flow and that the medium is incompressible. In the Maxwell equations, which is arguably one of the best approximations or the most valid assumptions, is that the magnetic and the electric field strength is small. So for the Maxwell equations, you will almost never get into a situation where field strengths are so large, let's say in practical applications, that you would have to consider a nonlinear version of the Maxwell equation. So that's probably, the Maxwell equation is an excellent approximation to the real world, whereas the Stokes equation, for example, is violated very quickly if you have flow that is only a few meters per second around a car, for example. So to show you this in the case of the Stokes equation, so the Stokes equations look like this. You've seen this before. So the Stokes equations say that the density of the fluid times the time derivative of the velocity minus the viscosity times the Laplacian of the velocity plus the gradient of p is equal to the external forces, so let's say gravity, for example, or whatever other forces you have. And then the second equation of the Stokes equations is that the divergence of u equals 0. That means that your medium is incompressible. So this equation, the Stokes equation, you can either directly derive it, or you can say it is in fact an approximation of the Navier-Stokes equation. So the Navier-Stokes equation have this additional term u dot gradient u here. And you know that the Navier-Stokes equation is typically used to model flow, let's say, around a car or around an airfoil, or well, any kind of flow that might show turbulence. So if you look at the Navier-Stokes equations, if you have slow velocities, then clearly the term u times u, so u squared, is going to be less than u. And in that case, so if you have small velocities, then you can neglect this term here, and you come back to the Stokes equation. When I say small, of course, what I really mean is that rho times u squared is less than, let's say, nu times u. That's sort of the approximation that's behind that. So the density and the viscosity clearly play a role in defining what small actually means here. So the Navier-Stokes equation is sort of the simplest nonlinear generalizations of the Stokes equation, and you can go beyond this. So for example, you can say, well, in, let's say, many real media, let's say in gases, the density that you have is in fact pressure dependent. So if you think about a gas, if you squeeze it together, if you increase the pressure, the density will go up. And so this term here will become a function of P, okay? But then also in that case, you need to replace the second equation by something like this, which says that not U is incompressible, the flow field is divergence free, but in reality, what you have is this equation, divergence rho times U. That is what we call mass conservation, okay? So in essence, what that means is that, let's say, if you compress U, so if U has a negative divergence, if you compress it, then rho in fact needs to go up. That's what's behind this equation here. So if you compress U, or if U has a negative divergence, if something flows into the volume, then the density of the medium in that volume needs to go up. So that's sort of the next more complicated version of the Navier-Stokes equation, and if you want to, you can just keep going. You can make it more and more complicated. For example, the viscosity might in fact depend on the pressure, or it might depend on the strain rate. So a lot of fluids have this property that if you have flow that shears the fluid, it becomes more liquid. So one typical example would be shampoo. If you shear fluid, so if there is a gradient in the velocity field, then the viscosity goes down. So in that case, the viscosity depends on the strain rate. There are other fluids for which the viscosity goes up if you impose a strain rate, and blood would be an example. Blood consists of red blood cells in the fluid, and if you strain it, then the red blood cells clump up and they increase the viscosity of the fluid. You can have many other extensions of the Navier-Stokes equations. For example, I could assume that the friction that you have in your fluid actually heats up the fluid. So if the friction is strong enough, then clearly the temperature will rise. So one of the things that you should take into account if you want to make it more and more realistic is that there is a temperature equation. For example, the friction in the fluid induces a change in the temperature, and then maybe the viscosity also depends on the temperature again. So let's say if you heat most fluids, then the viscosity goes down. Okay, so typical example would be, let's say you take something like Nutella, which at room temperature is pretty viscous, but if you heat it up, it becomes much more liquid, right? So clearly, in a case like this, the viscosity depends on the temperature, and so that introduces another nonlinearity because the viscosity appears in terms of the Laplace U thing. So if you have nu times Laplace U, and nu depends on the temperature, suddenly you have a T and U in one term, so you have something that's nonlinear. There are many other, like I say, many other ways how you could generalize these sort of equations, and in almost all of the cases that you could consider, ultimately you end up with terms that are nonlinear in the various variables that you have. Let me give you a second example. So in this first example, I showed you how to start from a linear equation and you come out with something that becomes more and more nonlinear. I'm going to show you an example that is sort of the classic, let's say, generalization of the Poisson equation, but I'm going to turn it around and I'm going to actually start with the nonlinear equation and show you under what circumstances we can get the linear case out of it. So if you think about a rubber band, for example. So let's say I take a rubber band, and I stretch it a little bit, and then I hold it between my two fingers, and I'm going to clamp it at the ends. And so if you clamp it at the ends, then let's say in the simplest case, of course, you would get a straight line. But let's say you apply a perpendicular force. So let's say you put a fan down here that blows hot air up, and maybe a fan down here or up here that blows air down, and another fan that blows up here. So the question is, how does this rubber band deform perpendicular to the original direction from here to here in response to this external force? And so what I would like to do is I would like to go through this modeling exercise. This is how we come up with partial differential equations, right, after all. So here's sort of the general approach. So let's look at a small delta x in the direction that the rubber band was originally stretched, okay? And so if the rubber band was not subject to external forces, it would just be straight, then along a delta x, the length of this rubber band would in fact be delta x. But if you do deform it, then there is going to be a delta u. And so here I already replaced delta u by u prime delta x, which for small delta x is true, but let's say in general, I could say this is delta u. And the length of this rubber band along this stretch delta x here, the length is then clearly square root of delta x squared plus delta u squared, and delta u is approximately equal u prime delta x. So from a modeling perspective, we can say that the energy that is stored in the deformation of this rubber band has something to do with the elongation. That's, and I'm going to assume that it is proportional to the elongation. That is, again, some sort of approximation that the elongation is not too large. This is what's called Hooke's law. So Hooke's law says that the energy stored in an elongation is proportional to the elongation. And I can calculate the elongation. That is, as I said, square root of delta x squared plus delta u squared. And then I'm going to add this up over every delta x from the left to the right end. So the deformation energy is going to be the sum over all of these delta x's from j equals 1 to n. So let's say there are n delta x's. Okay. It is going to be proportional. So my proportionality constant is a. And there should be a parenthesis here. So a times the actual current length minus the rest length, right? So the difference between the actual length minus the rest length, that is the elongation. So think about a parenthesis here and a parenthesis here. And then, of course, I need to make this delta x smaller and smaller. So I'm going to take the limit delta x going to 0, and what comes out of it is an integral from a to b. So let's say a is here and b is over here, of the elongation, and it is square root of dx squared plus u prime dx squared minus the rest length dx. Okay, I'm going to pull the dx out of this square root, and what remains is integral a to b, a times the square root of 1 plus u prime squared minus 1 dx. Okay, so that is the deformation energy, the elastic energy, and then there's a second part to the total energy that is called the potential energy, and the potential energy is essentially how much work did my rubber band do against the external force. So that turns out to be minus integral f times u. And the total energy then becomes this integral here. Okay. So you see already that the total energy is linear in u in this term, but here it is nonlinear. Now, how do I get a partial differential equation out of this? So nature seeks to find those places for which the energy is minimum. And so what I need to do is I need to write down the equations for u of x, or the equations that u of x has to satisfy in such a way that u of x is a minimizer of my energy here. And you remember this from your calculus days, that let's say if you have an energy, or let's say some sort of convex function, that the place where something is minimum is the place where the tangent is 0. So in other words, if you're looking for the point where all of the derivatives of your function are 0, right? So let's say in a one-dimensional case, let's say you have a parabola or something that is convex up. What you need to look for is that the derivative in this direction is 0. But if you have something like a two-dimensional case, so I don't know, a cone of some kind that is smooth at the bottom, what you need to achieve is that the derivative, or you need to look for a place where the x derivative is 0 and the y derivative is 0. Well, so in this particular case, you're trying to find a minimum of a functional e of u that depends not just on x and y, but on a whole function u of x. And so the natural generalization of this would be, well, it's an infinite dimensional problem. You're going to say that I'm looking for that place, I'm looking for that u of x for which e in every possible other perturbation in every direction, the directional derivative is 0. Okay, and so the way we write this here is going to be that I say that the limit epsilon going to 0 of, well, the perturbation is e of u plus epsilon v minus e of u. That's the rate of change in direction v. Okay, I need to take the limit 1 over epsilon of this change here, and I want this to be 0. So that is going to be what determines u, and it has to hold true for every possible perturbation v. So that's a natural generalization of asking that the gradient of a function is 0, for example. So if I go through the motions, if I put the definition of e of u into this thing here, and I just multiply it out, and I do, I take the limit, ultimately what I achieve is that I need to satisfy the following statement here, namely that the integral of a of b, a times v prime times u prime divided by square root of 1 plus u prime minus v times f equals 0 for all functions v. And I can rephrase this in terms of an equation. If I say, well, so if this has to hold true for all v, what I should do is I should get the derivative over here by integration by parts, and then I get something times v equals 0, and the something is exactly this expression here. So minus a u prime divided by square root of 1 plus u prime squared, and the derivative of this prime equals f. And then, of course, if you want to do this in multiple space dimensions, so not just for a rubber band, but in fact for something like a two-dimensional membrane, the natural generalization of this is going to be that u prime is replaced by gradient, and this prime is going to be replaced by the divergence equals f of x and y, or f of x and y and z. So that's the equation that comes out. So I'm not going to go through this. It's not just that I say formally, well, then clearly the natural generalization of u prime is gradient u, but I can actually derive this equation here directly from looking at the elastic deformation of a two-dimensional membrane. So this equation here is often called the minimal surface equation, and it's called that way because, let's say you assume that f is 0, but that you impose certain boundary conditions. So let's say you have your membrane, and instead of a drum where the vertical displacement is fixed at 0 all along the perimeter, if you deflected the clamping at the edges, so let's say you have something like a soap bubble or a soap film that is spanned by not just a circle, but by something that also has a vertical displacement. So the boundary values are not 0, but they are in fact something that moves up and down. Then this is the sort of equation that describes the vertical displacement of the soap film. It's called minimal surface equation because what a soap film tries to do is try to find that surface for which the total area of the soap film becomes minimal. And this is exactly the equation that describes this. Okay, so now that I've shown you the equation, let me show you what happens if we make the assumption that the membrane has a small vertical displacement and that it is smooth. Okay, so if the vertical displacement is small and the displacement is smooth, then u is small and the gradient is small, okay, so it doesn't actually matter whether I take the square or not. So if the gradient of u is small, so it's much smaller than 1, for example, then clearly in this equation here, 1 plus the gradient of u squared is in fact close to 1. And I can make the assumption that, well, this term here just equals 1, and I come out with an equation that approximates the original minimal surface equation that looks like this. Well, this is, in fact, of course, the linear Poisson equation, A being the elastic coefficient of my membrane. So if you assume, for example, that a membrane is spatially homogeneous, then A is just a constant, and I can put A out of this here, can divide F by A, and I get minus Laplace U equals some right-hand side. Okay, so in this case, I started with the real equations, and I made the assumption that the displacement is small, and then out comes the usual Laplace or Poisson equation. So you've seen now 2 examples where I have equations that are nonlinear. The question, of course, is, well, I mean, what's fundamentally different about nonlinear equations as opposed to linear equations? And I want to go through this in a little bit of detail because I want you to understand that there really is a fundamental difference that makes it conceptually and in practice much harder than just a linear equation. So let's start with this equation here. Okay, the weak formulation is that weak formulation means I multiply with a test function phi, I integrate over it, and then I'm going to integrate this by parts. So I get gradient phi times a gradient u divided by this term equals phi times f. That's, of course, exactly the variational form that we had a couple slides earlier. This is exactly this here, right? This is the one-dimensional weak formulation. It's not a coincidence. So this is the equation, and then of course the naive thing to do would be to say, well, let me take my usual finite element approach. I'm going to say UH equals the sum over j of coefficients uj, these are just numbers, times my shape functions phi j. I'm going to take this and I'm going to put it in here, and I'm going to test it not with all functions but only with the discrete test functions, and what I get is gradient phi I times this whole thing, where I've replaced UH by my sum, okay, equals phi I times f for all I equals 1 through n. And I mean, what I always do in that case is I pull the sum out of the gradient. I can pull these constants, these numbers, out of the gradient. I can pull the sum before, and I can put the UJs to the end, and I get this sort of thing. So I have sum over j of this expression here with phi I and phi j times uj equals something on the right-hand side. And if it weren't for this term here, then this would just be the Laplace equation, where the matrix that I get out is gradient phi I times gradient phi j. Okay, it doesn't seem fundamentally different, but the issue here is that all of the UJs actually appear in this matrix. Okay, so I get a potentially very large system of nonlinear equations, and so I could write this as, for example, A of u. So this would be my matrix capital A. This A has nothing to do with the elasticity coefficient here. Okay, so matrix A of u times this u equals f on the right-hand side. Now, we know how to solve linear systems. So when we had something like A times u equals f, there were all of these techniques like conjugate gradient, or if you want to, Gauss elimination, and so on and so forth. So all of these can help us solve these linear systems. The question is, what is fundamentally different about a nonlinear system where the matrix itself depends on the solution? And the answer is, the fundamental difference is that we do not have an algorithm that can solve these sort of problems in a finite number of steps exactly. So if you think about, let me generalize this a little bit more. Okay, so in essence, what we're having here is a nonlinear system. F1 of all of these variables equals 0, F2 equals 0. So I can write this as a capital F of x equals 0, and capital F is not just a linear or affine function of x. Okay, so the question is, how do we solve this? And the problem is, we do not have an algorithm that can solve it exactly in a finite number of steps. And I want to contrast this with with linear systems. So in the case of linear systems, you have Gauss elimination, which gives you the exact answer to a linear equation in n cubed steps if you have n variables, right? So if we could do exact arithmetic, we can solve linear systems in a finite number of steps exactly. Turns out that for general nonlinear systems, we do not have the equivalent of such an algorithm. There is no algorithm that can give us the exact answer for a general nonlinear system in a finite number of steps. Now, in our reality, this is actually already true if you have just a single equation f of x equals 0. So let's say you have an equation of the form, I don't know, x e to the x or x plus e to the x equals 0. Maybe that's a bad example. I think that actually doesn't have a solution other than x equals 0. But let's say something like x plus e to the x minus 1 equals 0. So a general nonlinear system in a general nonlinear equation in just one variable. Also, there is no finite algorithm to compute what we call a root. So a root of a function is a place where the function is 0. So since we don't have such a general algorithm, what we do in practice is we solve these problems iteratively. And an iterative algorithm means that you start with some x0, and then you compute an x1 and an x2 and an x3 and an xk and so on and so forth from this sequence. Okay, and the various algorithms produce these sequences xk differently. I'm going to show you a few examples. And of course, what we hope or maybe want to prove is that in fact these xk's converge to x, where x is a root of f. So I'm going to show this to you later on for actual partial differential equations, but let me assume really that the equation that I'm going to solve here is algebraic and not time dependent. So I want to come back to time-dependent nonlinear equations at a later time. So for the moment, really assume that this f of x, or let's say the capital F of x, the system of nonlinear equations that we have here, really depends only on these x's that corresponds to these expansion coefficients uj, and that there is no time derivative involved. Okay, so not something like the time-dependent Stokes equation, but more something like the nonlinear minimal surface equation. Okay, so what we want to do is we want to find a point x, a root of f, so that f of x equals 0. And the general approach to looking at these sort of problems, if you've taken an Introduction to Numerical Methods class before, is something that is called a fixed point iteration. So a fixed point iteration says, if we can, let's choose a function g of x in such a way that the x's that satisfy this equation, x equals g of x, are in fact the points where f has a root. Okay? So if you do this, then the question is, of course, well, how do I choose this g? And the answer is there are many different possibilities for choosing g, and I'm going to show you a few in a minute. But so let's say I have a g for which the x's that satisfy this equation here are also roots of f. Then I can do something that is called the fixed point iteration, which means if I have a guess, xk, then I can compute xk plus 1 by just applying g to it. And the thing that you learn about fixed point iterations in the Introduction to Numerical Methods is this iteration will converge if I can show that g is a contraction. So it doesn't really matter for the current purpose how that is defined, but that is the property that we need to have for g to show that it converges. Okay, so there are two steps in this process of finding a fixed point iteration. One is find a g so that the fixed points of g are the roots of f. Okay, so g clearly must be related to f. And then also you need to prove a particular property about g, namely that it is a contraction. Then this will converge, and it will converge to the root of f. So like I said, there are many different approaches to choosing this g, and I'm going to show you three that are of particular relevance in the solution of nonlinear partial differential equations. So one is what in the context of PDEs is often called a Picard iteration. Picard iteration really is just a different word for fixed point iteration, but in the context of PDEs we mean a very particular fixed point iteration. Namely, if this f can be written in the following way, namely as p of x times x minus h. That's a typical case. So if you go back to the equation that we want to solve a of u times u equals some right-hand side. Okay. So if I bring the right-hand side over to the left, then it would be a of u times u minus f equals 0, right? So this is a typical form for partial differential equations, some nonlinear operator applied to the solution minus the forcing terms equals 0. So if I can write this f in this form, and I choose my g as 1 over p times h, then this equation, x equals g of x, would be x equals 1 over p times h, or put differently, p times p of xk, okay, times xk plus 1 equals h. So this is what we call Picard iteration. And if you think again about this in terms of, let's say, matrices, solution vectors and right-hand sides, what that means is you compute the matrix by using the previous iterate as a linearization point, and then you have to solve a linear system because so xk is known, right? Xk plus 1 is the thing that you want to compute, so you solve a matrix for which that you know times the solution of the next iteration equals the right-hand side. I'm going to show this to you for the minimum surface equation in a minute. So this is what's called Picard iteration. It's one particular choice of g. Okay. A second choice of g that we often use would be that I say g of x equals x and then plus or minus some delta tau. You can think of delta tau as something like a time increment, a time step, times f of x. Now, the plus or minus refers to the fact I need to show that g is a contraction. So oftentimes I will be able to show that g is a contraction if I choose one of these two signs and I make delta t small enough. Okay, so that I haven't said anything about how large this delta t should be, but with a particular choice of delta t and a particular choice of sign, I will almost always be able to show that this g is in fact a contraction. So with this choice of g, I get something like this. So I get xk plus 1 equals g of xk. Okay, so that means xk plus 1 equals xk plus or minus delta tau f of xk. And if I bring the xk over to the left-hand side, what you see is that this gives me xk plus 1 minus xk divided by delta tau equals plus or minus f. So it's called pseudo time stepping because this here, of course, is something like a time, let's say, a discretized time derivative, right? So if I think of x as a function of tau, then this is exactly what I would get with, let's say, the explicit Euler approximation of the time derivative. So for these two things, you will ask, well, how exactly did I come up with these g's here? That doesn't make any sense. Of course, in reality, we start from over here. This is what we want to do. And then I'm going to find myself a g that facilitates that. Because in order to show that this here converges, I need to show that g is a contraction. So I'm going to rephrase this in terms of a fixed point iteration like this, and then I'm going to prove something about g. Okay. So these two methods here are pretty simple. I should say why it's called pseudo time stepping. So I told you that this is something like the time derivative with respect to a time-like variable tau. It's not a real time, right? I'm looking for the solution of a stationary problem. I'm just going to introduce something that looks like a time, a pseudo time, and then I time step it into the future. Okay, ideally until tau equals infinity. The third possibility is Newton's method. So Newton's method, you've seen this for one-dimensional cases, would be g of x equals x minus f over f prime. Of course, if you are in multiple dimensions, then 1 over f prime is not defined, but this would be something like f prime to the minus 1 times f. So that's the natural generalization of this ratio here. And then if you apply the fixed point iteration to this particular g, what you get is xk plus 1 equals xk minus f over f prime of xk, or in the multidimensional case, xk plus 1 equals xk minus f prime to the minus 1 times f. So let me walk you through this, how this looks like in the context of the minimal surface equation. So here's again the minimal surface equation in the strong form. The Picard iteration means that I have to, let's say, fix the denominator at uk, and then the enumerator would be uk plus 1. So this is a linear equation in uk plus 1, and I know exactly how to solve this. I'm going to multiply this with a test function. I'm going to replace uk by the sum of uj times the test functions. I'm going to pull this out. This gives a linear system in uk plus 1. It's like the Laplace equation, just with a spatially variable coefficient here. Okay, so this just becomes a spatially variable but known coefficient because I know uk when I want to compute uk plus 1. So we know how to do this. The pros and the cons of this approach is, so the pro, like I said, it's like the Poisson equation or the Laplace equation with a spatially variable coefficient. So it's like step 6. We know how to do it. The matrix is symmetric and positive definite. We can apply conjugate gradients for this, for example. It almost always converges. So I say frequently, so in this particular case, I'm pretty sure it will actually converge. If you have different equations, Picard iteration is pretty robust. Picard iteration almost always converges. The downside is that it converges pretty slowly. So oftentimes, if you have an approach like this, you need a few dozen or maybe a few hundred iterations until the uk plus 1 is in fact close enough to the exact solution u of this equation up here that we can say, okay, that's good enough. But oftentimes we need a lot of iterations for this. Pseudo-time stepping. So the pseudo-time stepping, like I said, essentially comes out of assuming that u depends on some pseudo-time parameter tau. We're going to add some time derivative here, and we're going to just compute it as in the limit tau going to infinity. So if I applied the explicit Euler method to this sort of equation, what I would get is uk plus 1 minus uk divided by delta t, and explicit means that I'm going to put uk here and here. Okay, so that is something like the something like the heat equation, except that this term is computed or has a different form than it has in the heat equation. In the heat equation, it would be just minus Laplace u, for example. So you know that, of course, for the heat equation, the explicit Euler method is not a particularly good choice. I think that's within lecture 26, for example, where we talked about this, or some time-dependent lecture where we talked about the fact that explicit methods for the Euler equation, the explicit method for the heat equation are not good choices because they require us to use very small time steps. So you can make this a little bit more useful if you make it semi-implicit. So I'm going to keep uk down here, for example, but I'm going to choose uk plus 1 in the enumerator. So I make it semi-implicit, so it would be fully implicit if I had uk plus 1 here as well. But by making it semi-implicit, the problem remains linear in uk plus 1, so every time step only requires me to solve a linear system, and that makes it more stable. So I can choose time steps that are as large as I want to, and in particular, of course, if I want to go with tau to infinity, then taking large time steps is something that I definitely want to do. I should mention this, so I can, of course, replace all of this by higher order time stepping methods as well. So for example, I could choose something that doesn't just depend on uk plus 1 but also on uk minus 1, uk minus 2, or I could do something like take the enumerator, and instead of putting uk in here, I could extrapolate from uk minus 1 and uk to the time tau k plus 1. So there are many options in which I can make this more robust or make it converge faster, for example. So again, the pros and the cons of pseudo time stepping is pseudo time stepping converges almost always. There are very few examples of equations, of nonlinear stationary equations, that you cannot solve with a pseudo time stepping approach. And so consequently, for some of the most complicated equations, let's say the Euler equations of gas dynamics, where basically every other approach fails, people use pseudo time stepping. So it is very robust. It is easy to implement. It's essentially just the equivalent of a heat equation. I can make every time step to be a linear problem, so it's not particularly hard to solve this. If I use an implicit method, I can make the time step larger and larger so that I get quicker to tau equals infinity, or at least the tau large enough. The downside is that in many examples, I need a lot of time steps. So let's say in the example of the Euler equations of gas dynamics, I might need thousands of time steps. Each one of these time steps is not particularly expensive, but I need a lot of time steps before I get close enough to the solution. So that's sort of the downside. So the last method that I want to show you is the Newton's method. So for the Newton method, I need to rewrite this a little bit, so I'm going to say that I introduce the residual R of u, which is just f minus, actually it should be f plus, of course, so I want to take this term here, want to bring it over to the right-hand side, so f plus this term here, and I want R of u equals 0, right? That means u satisfies the original minimal surface equation. So if you go back to the definition of the Newton's method, it said that uk plus 1 must be equal to uk minus, and then the generalization was r prime to the minus 1 times r. Okay. Of course, equivalently, I can bring this uk over here, so this would be uk plus 1 minus uk, and then I multiply both sides with r prime, so I get r prime times the difference, uk plus 1 minus uk, equals minus r of uk. And if I write this as delta uk, then I can write uk plus 1 as uk plus delta uk. So you've seen this iteration many times. This is what we use for finite dimensional problems, and this is what we use for PDEs as well. So without going into too much detail, so this r prime has a slightly complicated structure here. So if r prime is an operator, if I apply it to delta uk, I'm going to get all of this here on the left-hand side here. And I'm going to talk about how we get to this term in the next lecture. So it requires a little bit of calculus to get there. Okay. But then on the right-hand side, I have minus r, and with my definition of f, with the definition of r, I probably have a sign error here as well. I need to check this and correct the slides. It turns out that in this particular case, the operator on the left is in fact symmetric and positive definite. That should not come as a surprise because we're trying to minimize a convex energy. So r is already the derivative of the energy, r prime is the second derivative of the energy, so it is clearly symmetric. Like every matrix of second derivatives, of course, is symmetric. But then in this particular case, it is also positive definite, and that reflects the fact that we're looking for a minimum. So for Newton's method, the upside clearly is it shows very rapid convergence, quadratic convergence, and in the context of partial differential equations, I would say there are many cases where you can get away with 3 or 4 iterations. You almost never need more than 10 iterations. So it really converges very rapidly. The problem is that it converges only if you start close enough to the solution. So Newton's method can be shown to be a contraction under the assumption that you're close enough to the exact, or that you start close enough to the solution. And of course, we don't know the solution, so starting close enough is sort of a conundrum. We don't know whether a point where we want to start is in fact close enough to the solution. And there are many examples of equations where if you apply Newton's method blindly, then it will in fact not converge. So what people often do is something like they do, let's say, 10 or 15 or 20 Picard iteration steps, and then the solution hopefully is close enough, and then you do 2 or 3 more Newton steps and you're there. So you substitute the remaining 100 Picard iterations that only converge linearly by only a few Newton iterations that converge quadratically. The other downside is that, let's say, if you go back to the Picard iteration, the Picard iteration here had essentially, so the discrete form of this is essentially like a Laplace equation with this spatially variable coefficient. So we know exactly how to solve this. There is really no mystery about this. It's like the Laplace equation for all practical purposes. We can use the same discretizations, we can use the same linear solvers, and so on and so forth. But the equation that you have to solve for Newton's method looks a lot more complicated. So this is the term that we had in the Picard iteration, but then there's this additional term here that has a slightly more complicated structure. And so the question is not immediately obvious which solver is appropriate, what preconditioner, for example, is appropriate. So the operator has a different form, and we have to think about issues like the structure of the solver, the discretization, again, when we solve something with Newton's method. So it's a little bit more, there's more thought that's involved in this. So to sum this up so far is nonlinear stationary PDEs are difficult because there are no direct algorithms for to solve nonlinear systems of equations. We have to use something like Picard iteration, pseudo time stepping, or Newton iteration. And these are the 3 that we typically use in the context of partial differential equations. And they have the advantages that Picard and pseudo time stepping converge almost always, but very slowly, whereas Newton's method converges very rapidly, but you have to start close enough to the solution. That's the problem with Newton's iteration. So at the end of this lecture, I thought that I had more to say. Apparently that is in the next lecture. I wanted to say something about practical aspects, but I'm going to talk about this in the context of Newton's method then, and that is going to be lecture 31.55.